Okay, everybody. So let me share my screen first. Everybody, can you see my screen?
Yeah, sure can.
Yeah. Okay. So everybody see, here is the reminder about midterm exam 3 that will be held on this Friday, that is April 24th. Um, so although I have mentioned like 11:30 a.m. to 12:25, but I will make the exam available around 11 o'clock. So you are getting about 30 minutes. You don't need to take a printout because you can answer this time in your own paper. And the exam end time is like as usual 12:30. So I will be asking you only 3 to 4 questions. Although here I mentioned 4 questions, but even I might ask you only 3 questions so that you all are able to answer in 1 hour. This means starting from 11, so you can finish around 12:10 or something, and then remaining 15 to 20 minutes of your scanning and then upload on the Dropbox. I think that will be fine. And then regarding syllabus, you have to look all class lectures starting from 23rd through 31st. So 23rd, the class that includes the magnetically coupled circuits. And 31st, that will be next class. This means Wednesday's class. You have to look numerical problems, homework. In terms of book chapters, magnetically coupled circuits, two-port networks, Fourier series application to circuit problems, and three-phase circuits. So as you can see, 4 chapters. So either I will be asking you 3 questions or from 4 chapters, 4 questions. And then question pattern is the same as the first and second midterm exam. Um, I already posted the grade for the homework set 5. Have you all noticed your grade?
Yes.
Okay. And then actually, I am going to cover the solutions for homework set 5. And before I think I discussed solution for homework set 4, but I think I did not let you know the grade. So sometime today, you'll be seeing your grade for homework set 4 as well. Okay, so moving forward, so here you know that solution for homework set 5. And as I mentioned, I already posted that solution or eCourseware under the tab homework. So if you see, I think the last item is solution for homework set 5. So let me open that one. Hold on. Just a moment. Okay, everybody, can you see that homework set 5?
Yes.
Okay. So as you can see, so these are your questions. I mean, most of you have done well, pretty well, but there are some mistakes, especially in number 1 and sometimes in number 3. Everybody see the first problem was for the following circuit in figure 1, determine the coupling coefficient and the energy stored in the coupled inductors at t equal to 1.5 seconds. So this was the problem. And then you see, first you have to convert into phasor domain. So that's why you see the phasor domain circuit shows 40 at an angle of 0 degree, then 4 ohm, and 1 over 8 farad, 1 over j omega c. So 1 over j omega into 1 over 8. So 8 is going in the numerator. But you see here cos 2t, so 2 is the omega value. So if you put 2 omega value, then ultimately you are getting minus J4 ohm. And that 2 Henry J omega L, so J2 and 2, so J4. So and then this is 1 Henry and 1 Henry, so that is J2 ohm. And this is 2 ohm resistance. Now you see the dot terminals are given here and here. So I assumed the current in clockwise direction I1 and I2. So the first question was coupling coefficient, K value. So that is pretty much easy. K equal to M over root over L1 and L2. Directly the inductance value from the circuit, 2 and 1. So 1 over root 2 is 0.707. So everybody did that properly. Now you have to first find out the current I1 and I2, and then you can calculate the total stored energy. So everybody see for left side mesh or for mesh 1, see the equation. This is source minus to plus, so minus 40 at an angle 0. And then ion covers this 4 ohm minus J4 plus J4 that I have written. But on the left side or the mesh on, current is leaving the dot. But on right side mesh, current I2 is entering the dot. So it is opposite situation. That's why you have to give a minus sign. So minus I2 and J2, that mutual inductance, that equal to 0. And then I simplified a little bit. From here plus J4 minus J4 cancel. So 4 ion, then minus I2 J2, and I'm moving right side. That minus 40 becomes 40. So I just gave the equation number 1. Now from mesh 2, if you see the phasor domain circuit, I2 is 2 plus J2, and then again, because of the dotted terminal convention, mutual inductance effects minus J2 multiplied by ion, that equal to 0. So from here, I think I divided by 2 on both sides. So I2 1 plus J1, and I transferred it right side, so J1. So finally I am finding the value of ion. So I2, and then finally this is the value 1 minus J1. So now I gave the equation number 2, and I am plugging in this ion value in equation 1. So everybody see 4 into I2 into 1 minus J1 minus I2 into J2 equal to 40. And then if you simplify, I2 is the common factor. Ultimately, you are getting I2 value 5.55 approximately, angle 56.3 degree. And then plug in this I2 value in equation 2. So that will give you ion value 7.83, 11.3 degree. So these are the ion and I2 values. And then now, once you get the ion and I2 value in phasor domain, then everybody see here in the time domain, ion 7.83 cosine of 2t. 2t was the original expression, omega t, plus respective angle. You see here it was 11.3. And then for I2, 5.55 cosine of 2t plus 56.3 degree. Now, you are asked to calculate the energy stored in the coupled inductors at t equal to 1.5 second. That's why in the time domain function, put t equal to 1.5. So if you put t equal to 1.5, so that is making you 3. But keep in mind, this 3 is in radian, not degree. So in the second line, I've converted that 3 radian into equivalent degree. 171.89 degree, then plus 11.3. So then if you take the cosine of this combined angle, it will provide you some negative value, and after multiplying by 7.83 minus 7.82 approximately ampere. Similarly, I2 again in this equation, put t equal to 1.5, so 3, and then corresponding degree is 171.89 plus 56. That ultimately will give you minus 3.7 ampere. So now total stored energy in the coupled inductors, W half L1 ion square plus half L2 I2 square. And then here is the minus sign because of that dot convention. One current is entering the dot, other current is leaving the dot. That's why it is the minus. If it is the same, then it would be plus. And then I just plugged in those numbers. You see, ultimately, this should be the result approximately 39 point on. Many of you got 39.3, 39.4, but this will be the correct answer. Everybody understands? Is there any questions here?
No, it looks fine.
No questions. I see
If the
only
dots are on,
mistake.
oh, sorry, Carson. If the dots are on opposite sides of the inductors, that means you add the mutual inductance, right? Instead of subtracting it out, because the currents will be going same
Yeah.
directions.
Yeah, so therefore, for example, in this case, if you see that right side dot is on the upside here,
Mhm.
then it would be the plus sign because it's
Okay.
because ion current is leaving. Similarly,
Yeah,
I2 would be leaving because if it is here, in that
okay,
case, it would be plus.
that makes sense.
Or
Cool.
yes, okay. Or in other words, if you see that left side dot was on the upside, then ion was entering the dot and I2 is entering the dot. Then it would be the plus sign for the mutual. Is this fine, Nathan?
Perfect. Thank you. Yeah,
Yes,
that's
yes,
excellent.
yes. But probably you made on sign mistakes or something in your, yeah.
Oh, it was on the lab from last week, I think. There were a couple of them that I had done the math, but it wasn't matching my simulation, and then I realized it was because the dots were in the wrong place, and that's why it didn't work out right. And then I added it, and then it all worked out perfect. So I was like, okay, I see. But
Oh,
just making sure. Yeah.
oh, that is for the lab. Yeah, okay.
Yeah. Mhm.
So are you getting feedback about the lab from, we have one girl student, Javia Chaudhary, she is grading. Yeah. Are you getting feedback about the lab?
Yeah, I haven't gotten that one back yet. I think that one will be. I think we turned that one in Friday last week, so
Oh,
I'm
okay.
sure we'll get something back
Yeah.
this week sometime. Yeah.
I mean, I was asking her, she informed me that so far I think she has graded lab 4 and 5, yeah, probably. Yeah. Still, I think she did not grade fully the lab 6, 7 or the design 2, I think. Anyway, so she will be doing, and at the end of the semester, they will be, letting me know your overall grade, and then I will be looking finally when summing up with the theory. So you all will be fine. Okay, so moving forward, question number 2. That was about the transformer. It was pretty simple. I mean, most of you have done properly, but still I notice, I think 4, 5, some mistakes, a completely different number. Then please everybody see. The primary current to an ideal transformer rated at 3300 slash 110. This means 3300 is the primary voltage and 110 is the secondary voltage, is 5 ampere. So this 5 ampere is the primary current. The question is calculate turns ratio, the kVA rating, and then secondary current. So turn ratio, as you know, so V2 over V1. So many of you have done like V1 over V2. That is also fine. So I just kept in that format 1 over 30. And then, kVA rating is V1 ion or V2 into I2. It is the same. So in this case, I chose V1 ion because primary current was given initially. So V1 multiplied by ion. So in terms of kVA, 16.5. Now, secondary current, relationship V1 ion equal to V2 into I2. And both sides, the kVA will be the same. So from there, I2 equal to V1 ion over V2. So that gives me 150 ampere. So I believe everybody is fine with this simple problem. Okay, so number 3, so there are several mistakes in number 3. For the following circuit, in figure 2, find out the value of the coupling coefficient K that will make the 10 ohm resistance dissipate 320 watt. I'm sorry. So everybody see here that is the K. So some of you have assumed that this is the mutual inductance value. That is not the mutual inductance value. That is basically indicate that, okay, it is coupled. So there is a coupling of coefficient. That is the meaning this K. This is not the mutual inductance value, although it is placed in that way. So you have to understand by looking the symbol. This is not M, this is K. Okay, so this is the circuit, although in the solution I did not draw the phasor equivalent, but you have done the phasor equivalent. So first you have to convert all component into their phasor equivalent. So here one thing, so you have to assume that the mutual inductance is M. So therefore for mutual inductance, and you can assume that mutual inductance is in millihenry, because L1 and L2 are given in millihenry. That I mean that for M, mutual inductance J omega M, and because I am assuming M is millihenry, that's why I multiplied by 10 to the power minus 3 to make it Henry. And you see omega value is 10 to the power 3. Everybody see the voltage expression 165 cosine of omega t. So omega 10 to the power 3. So then if you multiply by 10 to the power 3, 10 to the power 3, 10 to the power 3 cancelled, and then Jm. So this means here for the mutual reactance term, it will be Jm, assuming M is in millihenry. And then you need to convert these two into reactances. So again, because this is 30 millihenry, so J omega L, so omega is 10 to the power 3, and this is millihenry. So ultimately you will be getting J30 and J50 here, and 1020 as it is. And here the source value is 165 at an angle of 0 degree. Now see the equation for the left side mesh, minus 165, because this is the source, angle 0, plus ion, so this 10 plus J30. And again you see, I assume the clockwise current direction, ion and I2. So ion is entering the dot, but I2 is leaving the dot, assuming that my I2 is also clockwise direction. So that's why minus Ji2M, that equal to 0. And then I am little bit simplifying. Ion 10 plus J30 minus Ji2. I just transfer 165 on the right side of the equation. I just gave the equation number here. Similarly, for the right side, this 20 plus J50 I2, and then minus JIM and the mutual inductance effect, that equal to 0. So from there you calculate I2 value. I transferred this term on right side, that's why it is JIM into M divided by 20 plus J50. I just gave equation number B. Right side, you know that there was one condition that I have put like in a short note on the left side. The statement was that will make 10 ohm resistor dissipate 320 watt. This means because on the left side mesh, we are assuming the current is I1. So therefore, assuming that that ion is in magnitude, that's why half ion square R equal to 320 from this step. So that's why you see the R value was given 10. So finally ion value is 8 ampere. We calculated, we will be utilizing these values somewhere later. So now see, now we have two equations, A and B. So what I'm doing, from A, we have ion and J, and I am plugging in J2 value from B into equation A. So look, I substitute M, right side is 165. And then see my calculation. Here J is J squared, that is minus 1, minus minus plus ion, M squared. This is denominator 165. And now I am just simplifying like simple algebra. So 20 plus J50. So this is going multiplied, this one plus this one. What I did, I think ion was the common factor here, in the previous term, ion. So I have taken ion here and I substituted the ion value 8 ampere from that left side calculation here. So that is 8. So 165 over 8. Now just cross multiplication. So you see this calculation, this multiplied by this one, plus m squared. Okay, and then this one, I think 20.625 is still 20 plus J50. And from left side, this is m squared, I have written first, and minus 1300 minus 1500 plus 200 plus J1100. And you see, this is cross multiplied, this one, real term, reactive term. And then I am taking the magnitude because on both sides it is the complex variable. So I'm taking magnitude. So this real number is squared plus imaginary number is squared. Similarly, right side, real number is squared plus imaginary number is squared. And after that, I made a square on both sides. So then root sign cancelled. And then left side, I'm keeping this one, and then I'm transferring 1100 squared right side, this one minus. I put the squared value, and then left side this one, right side this one, and again I am making root. So I am getting m square minus 1300 after square root. This is the value. So m square after moving this on right side, ultimately m value is 38.13 millihenry. And once you get that m value 38.13 millihenry, then calculate the k. So m over root over L1 and L2. So m is in millihenry, and then L1 L2 is millihenry as well. So finally k value is 0.984. Everybody understands this one? It's just, a little bit long calculations, but just algebra. And then you have to do it carefully, as long as you are writing the equations correctly. And if you don't make any mistake in any steps, the calculation, then you should be getting the right result. So many of you have done this one properly, but in some cases, I think 5-6 cases, you got completely wrong result. Okay, so moving forward, this one. Calculate ion and I2 in the two-port network of figure 3. So you see, so on the left side, there is a voltage source 2 at an angle of 30 degree, 2 ohm resistance, the ion current entering. Here the voltage is V1, and then those values were given, impedance parameters, G11, G12, G21, G22. And on the right side, this is short circuited, and then I2 current is entering and voltage is V2. Now, first write down the equation. V1 equal to, G11 into ion. So here that G11 value is 6, an ion. Plus G12 into I2, but G12 is minus J4. So I2. That is one equation. And similarly, V2, G21 into ion. So G21 value minus J4 ion plus G22 into I2. G22 value is 8. So these two are the basic equation. But now you have to put the V1 and V2 value. So therefore everybody see, here is the V1. So there is a source and there is a drop here, voltage drop due to ion. So that's why V1 is 2 angle 30 degree minus that 2 multiplied by ion. And then V2, because this is short circuited, it is 0 volt. Now plug in those numbers. So therefore from on we get, after plugging V1 value, this one. After simplifying, this is one equation. And from 2 we got, after plugging in V2 equal to 0 volt, I2 is this. I am plugging in I2 in equation A. Finally, I got ion either 0.2 at an angle of 30 degree ampere, or you can express in milliampere 200 angle 30 degree. Similarly, I2, after plugging in I2 value here, you are getting 0.1 angle 120 degree or 100 at an angle of 120 degree milliampere. So therefore, most of you have done this one properly. Although like I think 2 or 3 cases there is mistake. Everybody is fine with this problem?
Yeah, it looks good.
Okay, great. Yeah, then the last problem, obtain the G parameters for the following network in figure 4. So this is the network. So to find out the G parameters, first I have written down those common equations, V1 and V2. And when you will be calculating G11 and then G21, you have to make right side open, right side port open. That's why see my diagram. On the left side, I have assumed a voltage source V1 current ion is entering. And on the right side, it is open circuited, but there is voltage V2. This means current entering I2 is 0. Now, under this condition, you have to find out G11 and G21. So everybody see from this circuit, G11 is V1 over ion, assuming I2 is 0. So you need V1. So everybody see, here is the V1. So what is that V1? V1 means ion multiplied by the equivalent or the total impedance of the circuit. So that's why everybody see, on the right side I have written V1 equal to ion multiplied by G, that capital G. This means this G is the total or the equivalent of the circuit. So I am calculating G. You see, if you see the circuit, 4 and 2, this is in series. Then this 6 is parallel in 6. And then that combination is in series with 1. So that's why I wrote 6 parallel 4 plus 2 plus 1. I am getting Z equal to 4 ohm. So therefore, I have written V1 equation, ion multiplied by 4. So therefore, now come back in the G11 expression, that 4 into ion V1 value. And ion as it is, ion cancel 4 ohm. This is one answer. Now you need G21. G21 is V2 over ion. So what is V2? Everybody see the circuit. Here is V2. This means voltage across the 2 ohm resistance. So therefore, first you have to find out what's the current flowing through the 2 ohm. Now see the circuit, ion current is entering here and it is dividing into 2 parts. Something is going there and something is coming here. So I just applied the current divider rule here to get the current flowing through 2. So I am doing it here. I do total current multiplied by this 6 divided by 6 plus 6, that is the 12. So this means ion over 2. So and then V2 is 2 multiplied by I2. So 2 multiplied by ion over 2, 2 cancel. Ultimately that is the I1. So that's why ion cancel. So 1 ohm. Similarly, for now to calculate G22 and G12, we have to assume that the left side node was open in the circuit. This side is open, but there is a voltage source on the right side node number 2. So I am putting voltage source on right side. Current I2 is flowing. Left side, there is plus, minus, and this is the V1 open circuit. So G22 is V2 over I2, assuming ion is 0. So therefore now what is V2? Here is V2. V2 is, you see, I2 multiplied by the impedance. I2 multiplied by the impedance. But here what is happening? Because no current is flowing through 1 ohm resistor. So you don't need to take that into account because you are looking from this side. So 6 and 4 will be in series. So 6 and 4 series is 10 and then parallel with 2. So that's why G is 10 parallel 2. So it gives me 1.67 ohm. Now what is V2? The total impedance multiplied by I2. So my V2 is this. Now substitute this V2 value here. I2 multiplied by 1.67. And I2 it is as it is. So I2 cancelled 1.67 ohm. Now G12 is V1 over I2. So what is V1? If you see this one, so V1 is here. So because no current is flowing through 1 ohm, this means V1 appears across 6 ohm. So you have to find out how much current is flowing through the 6 ohm. This means I2 current is entering at this node and it is going this way and this way. So you have to apply the current divider rule to find out the current flowing through 6 ohm. So that's why I have written here, you see, I6 total current multiplied by this impedance and divide by this plus this. So 6 plus 4, 10 plus 2, 12. So it gives me I2 over 6. Now, what is V1? V1 is that 6 multiplied by this I6. So 6 multiplied by I2 over 6, 6 cancelled, I2. Now come back to this equation. So G on to V on is I2 over I2 1. So this means you got all 4 impedance parameters, G1 G2 G12, and then G22. I think many of you have done this on properly, although there are few mistakes. Everybody is fine with this one?
With that one, is it easier to just convert it to a Y from the delta configuration? Because then you just have a series circuit for both sides. That's what
Yeah,
I did.
yeah, no, that is fully fine. That is fully fine. Yeah. I mean, as long as everything is like reasonable that you are making, so you are fully fine, no problem. And then many of you have got properly the correct result. Okay, so sometime today, I think within evening, I will upload your grades for homework set 4. Although I already discussed the solution for homework set 4, but I am going to upload your grading for homework set 4. So then you are like fully ready for the midterm exam 3. Okay, then so today I'll not be going over any new things. So I am stop sharing. Does anybody have any questions and comments? So I would recommend everybody, please try your best to do very good in the third exam so that you can cancel your first exam. So then I can pick up like number 2 and number 3 as your best on. Please everybody try your best. These 4 chapters, magnetically coupled circuits, 2-port networks, Fourier series and 3-phase circuit. And in that way, like you are covering the whole syllabus and then like you are ready for the final exam. Okay, so with that, like I like to conclude here. So everybody, so have a good day and please be safe. So see you on Wednesday.
Thank you, Dr. Ali. We'll see you Wednesday.
Okay, see you.